Thank you. So actually, we're going to wind up talking about it in rather conventional ways. At the end of the day, we're going to tie this back to all of the. One of the things I find is that people feel that they lose all the tools they've had and all the skills when they move to event modeling with events versus their normal form and tables. So before we get into that, I'm going to do a little bit of a background on why we do these things and how to break things down because it answers a lot of questions. So, what we really want here is we want simple, scalable applications, right? And what gets in our way primarily is a little bit confusing. So, the enemy is that we start with one thing and we add another thing, and the connections between these go up based on a factorial. The permutations make things incomprehensible. And this is what we're trying to address, especially as we add in the complexities of distributed applications, of high scalability, and we get this. I'm sure everybody recognizes this. I got this out of Redgate. This is a real production database. I'm not going to say which one, but that right there is the one table in the middle that controls everything, and these are the store procedures that go around it. This is what we're trying to avoid. So I was sort of hilarious, as a joke, put together Condron's law. The one thing I want everybody to understand is that as soon as you get to 5 interconnected components, the system is incomprehensible. There's a corollary that we can make things comprehensible by reducing allowed permutations. What does that mean? Everyone, I imagine, recognizes a layered architecture. We have a UI, a data layer, and then storage, right? We can go even further, and we can make everything one way. So this is really, when you hear people talking about CQRS, this is what the core goal with CQRS is in distributed systems. Think of each one of these as one of your microservices. How do we get this to work, right? Because once we can do that, now we can make pipelines, and we keep that simplicity. And we can do scalability without getting back into the complexity. So that's what we're trying to do. We're trying to get away from these complex systems that are all interconnected, these monoliths, and create these simple systems. To do that, we need to look at our storage, right? Relational storage, that's one of the core types of storage we have. It's designed to build tables and relate things, connect them together, not what we want. We've got graph storage. We've got document storage. Document storage helps a lot with simplicity. But one of the things that we started with 50 years ago that we've forgotten is that ordered storage. Writing things down in order is one of the core methods of storage that we have. And it still exists. We still use it, just appending things in order to a log. And there's several classes of ordered storage. There's the log, right? Just unstructured data. The log doesn't care what's in it. Anytime you log out data from an application, that's what you're using. This is the foundation, right? Then we have the ledger. A ledger has the same properties and it's still ordered storage. But now what we're saying is that everything that we write down is a transaction. So we've limited everything and we're putting more constraints on what's in there. And then the last thing is an event stream. This is an example of an external event stream of stock tick prices coming through. And then we're going to see that come up. So event storage systems are a class of ordered storage. And what we want is in our CQRS design, we're looking to write things into ordered storage, particularly event logs, to help us simplify that one-way path. So there are 4 application storage patterns that use event streams: command sourcing, change logging, state logging, and event sourcing. And given some of the early definitions of event sourcing in the space, that gets confused a lot. And so if we're going to define and model events, we need to understand which one of these that we're using. So I like to use this picture here. Normally, if we were in person, I would ask anyone to recognize this. This is a physical model of a Turing machine, the foundation of all of our computer science today. If we have a tape, we can write on the tape. This machine can back up and rewrite on different parts of the tape. But what we're doing in event sourcing is we're doing a one-way Turing machine. We're saying that we're writing immutable events and publishing them out. That's our ordered storage. So rather than going back and rewriting, we're just going to move forward, and we can replicate anything you can do with a Turing machine, we can do with a one-way Turing machine. So that's the foundation of what we're doing. So what we get is we get an event writer. You'll probably have heard this called an aggregate. It's the same thing that a process manager does. A microservice that writes, an event source microservice. We have an input, we have an internal state, and we have an output. And we read our own history. So we're using an ordered storage persistence mechanism behind a logical Turing machine, right? And this is what all of our microservices, all of our aggregates, all of our compute is going to be using the same pattern, right? And what kind of sourcing we're doing with our ordered storage depends on which part of this state machine we store. If we store the inputs, we're command sourcing, right? So if you save your commands, that's command sourcing. Command sourcing can be very powerful in occasionally connected systems. If I want to have something go offline, listen to, take some state with it, have users save their operations and come back, because we've disconnected our core storage, we don't really want to save the events they created because we don't know if they're valid. We want to save their commands and then reapply them when they rejoin. However, we cannot understand our history in this model without understanding our machine, because what these commands do is tied into the machine that we're using to write. And that machine, anytime it changes, we get into trouble. The key here to remember is that version 1 and version 2 of your software is a change in the machine. So as we try and send out updates, understanding that command log is going to become more and more difficult. It's not awful, but it's more and more challenging. Saving the internal state. This is often change data capture, or what I call state logging. So change data capture is we take the deltas of whatever's in there, and that's what we're storing as our state in our order log. State logging is we take the final output state of what's inside the system and we save it. Neither one of these both suffer from the same problem as commands, being closely coupled to which version of the service you're running. Thank you for that note. A transducer is the formal name of a one-way Turing machine. That's awesome. Thank you, Thomas. So if we're saving the internal state, we have thrown away tremendous amounts of context if we're just saving deltas or end state because we don't know how we got there, and we are tightly coupled to the version of the machine that we're running. Event sourcing is saving the output, right? So what we're saying is the decision that was made by the machine is what we are saving in the log, not its internal state, not its current state, not its input. And in particular, for event sourcing, the schema of what's in the database, what's in the log, is versioned separately from the service. you should be able to, the litmus test is the events that you write into the log should be intelligible by the business without understanding the services. We want events like item purchased, transaction complete, amount reserved. These should be business operations. This is going to give us two benefits here. Well, actually, a bunch of benefits, but it means that we're not tied into our particular implementation. And it also means that we can write new services that operate on the stored data differently than the services we wrote the first time. So now we can do upgrades, changes, and additions, and we can allow these services to vary at a faster pace than our data. So we want to model our data to the business schema, not model our data to the current version of how we're achieving what's been requested. And that's a really big difference. And that isn't really possible to do with change data capture, with state logging. It is somewhat possible with command logging, but you still won't get the same reports and results. So one of the goals here is always in my mind, I think about if I was going to do an enterprise report, what I find is most of the time the business really wants that report to read the same thing after a rebuild, right? So if we want that to work, we need to make sure that what we have is repeatable. So event sourcing, formally defined, application decisions are persisted as an immutable sequence of business events. So we went through all of this to understand why we're trying to do event-driven systems, why we're trying to do event sourcing, what event sourcing actually is. So now we have a framework for what it is we are trying to model. We're trying to model the business events, and we're trying to do the same work that we did when we did a third normal form model and created an ER diagram. We're now doing that in our events. So, stream database. How does this database work as we write these events into it? So what we've got individual streams that we're going to be writing our events into. So we target a stream, we write event one, and what you're going to see here is that each stream has a sequence number, which is the same as a primary key that's auto-incrementing in a table in a relational database. Every stream is going to have an auto-incrementing position, 1, 2, 3, 4, 5. The events that get written in, this is the global order here. One, I wrote this event 1, and then I wrote into stream 2, then I wrote back into stream 1, right? And you can see that I have an event log that contains all of the events in order, but I still have addressable streams that have the individual events, right? And then I can also create the equivalent of a view, which is what we refer to as a projection, that is a reordering of the events in the streams to some new ordering or some new selection of those events. It's equivalent to a custom view or a custom index because it combines the ability to read those quickly and a custom view of that data with a name. So event-sourced applications, as they use this structure, what you're going to find is that each one of your writers gets targeted to a single stream, right? So it's going to have one stream with a guaranteed ordering incrementing position that it writes to and it saves all of its state in. So this is why it is okay with event-sourced systems and event stores to have multiple microservices all writing into the same store. So it's generally considered to be a bad idea to do this with other stored systems. If you have all your microservices into the same store, the same database with a relational databases are designed to couple information. They're going to wind up naturally bringing the state of all of your event source systems, or of all your microservices, together. Here, the fundamental approach, because it's isolated and immutable and appending, makes having different microservices all writing into the same store work very well. And that could be a pool of the same sort of service that are all operating on a class of object, or it could be different services that all need to have a global state in order to create business context, right? And again, you can also scale out and have as many stores as you want. The key here is that you can have different stores, different services writing in the same store. On the processing side, it's very different though. The output, the read models, pushing into whatever derived state we want to generate. This could be caches, this could be other data stores, this could be screens. They have the ability to read across the entire log safely. Because everything is always appending, this solves a lot of the cache invalidation problems that we see. It's one of the hard problems in computer science, is how do we do cache invalidation? How do we know when our cache is good? And what we say in event source systems that have this increasing and incrementing structure, we say that we're always good, but we may be stale. So we only need to update the cache when new information arrives, and we can set SLAs, and we can monitor how we consume that information. So this allows us to be real time, allows us to be reactive, right? And it simplifies our scalability, as we saw with the pipelines, and it's going to simplify our entire system. So what we say is that a microservice in this pattern is only, its decisions are only valid upon commit to the store. So once the event is written to your permanent store, then it's available for anyone else to read it. That's our commit point. We can also use that position in the stream to do optimistic concurrency, which saves a lot of complexity as well. So we don't really need to go through this. This is what you're looking for in an event storage system, but that's not the focus. So we've got our event store. This is a very primitive view of it with fine-grained streams and event log. One of the things that we find as we get into data modeling is we find it's very, very useful to start creating categories. And what a category is I've got a core log, and then we're going to see that I've got a category foo, and I have instances of foo 1 and 2. I have a different category bar, and then instances of 1 and 2. So this category might be invoices, foo might be invoices, bar might be users. So I could have invoice 1 and invoice 2. You'll see here that the category is dotted here because it is a projection. We write into the instances, and that goes into a core log, and then the category is a logical container for that data that we write. So now we've got our structure. We know what we're writing. Now let's go back and take a step back and take a look at how data modeling was done when relational databases were new. So it's really about tuples, right? The original COD definition of a tuple is that these elements across this table, the ID, the client ID, the date, and the description, form a tuple, right? And that tuple, we then, in a relational database, for efficiency, all of the tuples have the same schema definition, which is the table, and then the table groups all of those tuples together. So we have one tuple or one row. So in relational databases, a row is a tuple. The schema of the tuple is the table definition. And then with the IDs that we have are an ID per row. So with third normal form, this is a structuring methodology for private data that says we're going to take and we're going to break our table schemas so that there is no duplication of data between our schema definitions. This is the ideal form for internal modeling. Well, I want my application to be using a non-overlapping, very efficient schema of the style of third normal form. So here we see that I have invoices, I've got a primary key, the ID, and then I have another table with line items. Those have a key that matches, and so we have our primary and foreign key relationship, and then I have more information here. You can see I have, invoice, these first three rows go to this first row in the invoices table. This fourth row here is related to this row up here. Down at the bottom, I only have reference to one of them, right? And that's the first one here. But we also have a relationship with the client ID to an entirely different set of tables. In this case, it's only one for simplicity. Customers, right? And each one of these, again, has an ID, and then we have data. Now, one of the challenges we find here as we dig into this is that this allows not only, this allows good storage, but it allows updates on the existing data. So what we want to do is we want to find the categories for that data. Because in event sourcing systems, what we do is we take the categories that we have here, and where rather than enforcing the schema per table, what we do is we define a set of schemas for the events that are allowed in a category. So that means that we say, so we're going to turn it on its side a little bit. The way I think about it is each one of these rows now gets a stream behind it, right? So it becomes three-dimensional with a history behind it. And then rather than limiting ourselves to a single schema definition, we're going to have a set of schema definitions that all relate. And that new structure is a category. So the categories that we see here are customer and invoice. And what we're going to do is we're going to take this and we're going to break this down to two different categories. So now what we're going to see is that in our model here, I have two customers and I have two invoices. So if I divide this into a customer category, I get customer 1, customer 2. I'm then going to see a series of events that represent the same data and the same tuples that we saw in the table, right? So if I look here, I've got ID, name, type, and payment terms. Add customer, Bob's Tire, commercial, net 30. One of the other things that we are doing is that as we are creating this change, the operation that we are putting into this table, we are actually going to name that operation and we're going to give it a business name, right? We aren't going to use add or update or change. That's a database definition of what we're doing. Instead, what we want is a name for the operation. And again, as we saw before, it needs to be in business terms. So we're going to add customer, and then we're going to put that tuple in. So add customer will have a defined schema. That schema contains those 4 items. And then what we're going to do is here we see this would be an update. So this is an insert. This is an update. The update here is term extension negotiated, and we change the data from net 30 to net 90. And here in this table, there's nothing here that tells me we went from net 30 to net 90 on this first customer. But here, I can see that I made that change. And on customer 2, all we have is a single add customer. Now let's go to the invoice. This is where we're really going to see the different the different schema types coming together into one table from what in third normal form would be multiple tables. So here I have invoices. I've got the first definition of invoice table, and then I've got line items, and I've got a payment status. So here, invoice 1, we have add invoice. Again, we see the data is the same. We have add line item, right? This adds a line item table. We add 2 more line items, and we can see that at this point here, we have the schema from invoices, the schema from line items. The names of the operations are all mapped one-to-one. One of the things that we're doing here is, even though we're using a JSON schema for the events, when we're doing formal data modeling, we want to keep the members on the event to simple types. Otherwise, that's the equivalent of adding a blob field to your schema. You can do it, but it's not part of formal modeling of what's going on. So then we take a look at invoice 2, right? And we see that we have this status here, but it looks like we only have 1 line item, nothing's been paid, right? But here in our history, we're seeing that we have add invoice, add line item, we added a second line item, and then we removed it. So we're keeping that history inside the table. And then what we're going to do, now that we have everything divided into instances which map to our primary keys, so the primary key here becomes an instance of a category, which is a set of tables. And this, one of the powers of this is there's lots of good ways to do this modeling, but I always have trouble defining people what's a good event and what's a bad event and what should we be doing. With this set of definitions, you can now say what is a good event and what's a bad event. Third normal form tells us don't repeat data. We're going to keep simple fields on the events. There's some other rules that I'll give later, but this all helps quantify with well-known existing tools what is good and bad data modeling in the system. So now one of the things we can do is we can also take a look at the simplest possible read model that we can do out of a category or out of an instance in a category. And that is, all we do is we do a union of the fields that we provided across all schemas. So one of the things we're assuming here, to be clear, is that when I take these 3 schemas and I say they're all in invoice, I'm assuming this date is going to become invoice date if we need a different date. That any one of these schemas I pull together, the columns across all of my event schema definitions are unique and for this category, right? So that if I come down here to the union, all of A are the same. So if I have an event here that updates the same value twice, I'm going to assume that's a replacement for that value. So the simplest way to look at it, one of the simplest ways to look at it, is as a sparse columnar database wherein the events are inserts into that column and current state can be recognized as the most recent value for all of those. Now, there are far more complicated read models and derived states that you can build from this, but this is a very good way to test your model to make sure that you don't have overlapping or conflicting schema definitions in the set of events that you've defined for a category. And it gives you a very simple readout on quote-unquote current state. If you were doing something like having an aggregate, this could give you a current state of that aggregate in a very simple model. Whereas we're just saying everything that gets written in events is a replacement. Best practices, and this is all in terms of your internal online event processing model, right? This is your OLTP for your application. We're going to talk about public-facing models separately. Step 1, keep it sparse. Don't have any additional unnecessary data on any event. Write it down once, and that's it. Read-side systems can access any data in the system. caching is a solved problem here, and you're going to get live push. So just run it once. Just because you need something on a screen, don't put it in an event. It's one of the biggest things I see people do. If it's written down once, that's it. Don't use flag fields. Don't use noble fields. The reason for this is that flag fields and noble fields are generally used for hierarchy and table modeling. They generally mean that you are putting more than one conceptual object into the system. So as a best practice, don't do it. Are there times where you have to? Of course. But it's generally a smell that you haven't actually modeled the two separate things correctly. So go through and do the modeling. The second thing is that we are now fundamentally moving to a history-based modeling. Model what has happened. Don't model just the current state. Don't get focused on, because this is what we focus on in relational, this last current state. Model how do we get there? What are the operations of the system that we're going to make a change on? Don't try to couple or build things together. Use surrogate keys for things, and the application will enforce them. That's the way you want to do it. And again, I'm going to repeat again, don't put data in something just because I want to display it. That's the job of the read side generation, not the job of the write side. Additional data concerns. So one of the things that I get all the time is, well, isn't my data going to explode, right? Aren't we going to have just tons of data that's going to build up forever, and how's this whole thing going to be untenable? I'm assuming most people at this conference don't have that concern, but you're probably going to face it. One of the things that we look at all the time is we see this nice third normal form ER diagram up on the wall. But what we don't consider when we look at that design is in any large system, we're probably going to have history tables. We're probably going to have audit tables. We're probably going to have reporting tables, right? And then we might have some publishing schema. So inside that database, you're actually wind up with multiple duplicated schemas where that data has been copied and moved and copied and moved. By moving to a third normal form, sparse model, even though we've included the history, one, our history is going to be accurate, which I've never actually seen in other systems. Two, it's actually going to be the sparsest representation of that history that's possible. So in production, if it is well modeled and retention periods are set, I actually find it is smaller in size. The other thing is closing the books is a key pattern that we want to do here. And that is taking a business period, taking the entire store from that period, marking it as archived, copying entries forward into a new store, and then starting the process again. We want to, again, align this with the business period, not with the internals. We want to say, is it quarterly? Is it yearly? I've seen systems where it's daily. But formally model that retention up front. I've seen giant relational databases that we get to the point where, the data business now wants all data older than 7 years removed. You can't do it. The system, just because the planning wasn't done, you have the retention problem. So do the retention planning up front. How much do you need? And those old stores are still available, but their role now is for archive and audit. So their SLAs are different, and they can go on cheaper storage. The other thing it allows you to do is, if I've rolled everything forward to a new store, I don't need to worry about the schemas in my old system. So the long tail of schema modification gets cut short every time you roll the system, which can be fabulously really good for development. Estimated stream length. In any system, you would never want to have a single table with all of the data in your database. Same thing goes for event source systems. Design your streams, figure out how much data is going in, look at the rate of data production, the rate of data retention, and how you're going to use the data. All of these can be brought into stream design, right? If I've got a system where I'm doing, say, identity, and I want to track every login, and I want to track when last time your password was reset, one of those is going to change much faster than the other. Those should be in separate streams, right? I can also divide streams by day. I can say, here are all my daily transactions, and I create a new stream every day. Designed for that length, and you're not going to get into the classic, well, what if I have to replay a million events? If you have to replay a million events to reset current state, either something's gone really, really wrong and you've lost all of your caches, or you designed your system such that you needed something all the way at the back of the beginning that probably should have been in a different stream. Personally identifiable information and GDPR. Separate it out. It doesn't matter what system you're in. All of the personally identifiable information should be in a separate stream in this system with a surrogate key to the primary information about that customer. Customer 952 should never be deleted. We should be able to delete all the information that tells us who customer 592 is. That way, our system still works and we can remove the data. And even if you're going to do crypto shredding, that separation of concerns and upfront modeling is really how you're going to win that battle. Log scope. We don't want, I've talked earlier about the ability to put different microservices all into one store, but we don't really want that. How much global ordering do you need? Where are you going to start sharding? If I've got a distributed worldwide banking system, I don't want to lock transactions in New York based off transactions in South Africa or in Seattle, right? What I want to do is I want to say, okay, all the transactions on this institution are going to be in one log so I can get a guaranteed daily balance. I'm always consistent, or maybe not even the whole institution, but some subset of it. But then I can have another log that has the same scope in a different location. Design the scope, you're going to find the business will have done this already for good, solid business reasons. Find those schemes and follow them. The last thing is the public and the private schema. As anyone's ever worked in a large enterprise could probably tell you, even in the world of relational databases, you don't want other projects accessing your private third normal form data, or you need to change something, and as soon as you're going to do it, you break them. The same thing happens in event source systems, and this is really the start of the distributed monolith. The way to solve that, first and foremost, is separating your public and your private schemas. All the rules I've given you now are about how to design that private schema for your application. Your public schema follows first normal form rules and follows the rules around good API design. A local API should be fine-grained, right? And lots of calls. A public or foreign API to a different system should be coarse-grained, should have all the information so repeated calls are not necessary. So we want to take our private event schema and create a public event schema that is coarse-grained and has large updates and will duplicate data. So we're going to send an update, which is that current state. So before, I'm not going to try to scroll back, where I talked about state logging is not how you want to event source. State logging is a great way to do public publishing of your internal state to other consumers. You want to model that state for what they need to know about your internals. So you want to edit out your internals from it. But that we take our current state and we publish it again and again and again with sequence number is one of the good patterns you can use. So what this means is I've got here, I'm using the hexagonal architecture pattern here to indicate that I've got an application with a writer, an event store, and a processor, anti-corruption layer that then publishes onto my public bus. This is where things like Kinesis and Kafka are going to be awesome. So you want a fine-grained database to be your event operational store, and then you want to distribute on something highly scalable. The schema for what goes on to that public bus that you're distributing to all of your other processors and microservices that are outside of your application space, right? That needs to be defined carefully because it's going to live a long time. And you're likely going to be supporting multiple versions of that schema at the same time. So what I want replayable application spaces with a dedicated store. And in here, I've got a single writer, but this could be a whole pool of microservices that are all on one topic or one thing where either reports or other things need that global state between them. And also because we are doing append only, we can support much higher levels of concurrency in writers and still maintain that global ordering, which is often not possible in something where you're going back and updating things. The append only, forward only motion. And you also get a very low impedance with an event source internal to an event sourced external distributed architecture. So you don't have to figure out how do I turn things back and forth. To Thomas's question, the heuristics, I'm not sure what you're looking for there, but the classic definitions for first normal form and third normal form, where in first normal form, I want everything a consumer would need to be available in the update. So I design the internal events based on the needs of the application, everything we just walked through. The external events, I design on the needs of the consumer. I say, when a consumer gets this update, what is the list of things they need to know about? And then I'll aggregate together all of the related consumers and create one common schema that I will update and republish again and again. Now, another key aspect of that is, whereas the data inside is a permanent historical store, the data on the outside is derived data, and it should assume to be transient. Now, you're likely going to want to keep it for a month, keep it for a week, but it should always be able to be rebuilt, and you shouldn't worry about duplication. So you're going to repeat and duplicate things. Yes, consumer-driven contracts is the right way to look at your public schema, right? Design them for what they need. Never have them need a second call. That's how you want to do that. So how do sparse events relate to, don't forget what you already know when it comes to read models? Sparse events internal to the store. When I'm building read models, I'm always assuming that anything other than a trivial read model will have a cache. So when I'm creating a read model, that's different from publishing a public event, right? I would probably use a cache to do that. But what I'm going to wind up doing is keeping those values. Once I've read them, I'm going to keep them around, and I will do updates into my read models. Read models are derived data. They can be overwritten. They can be changed. They can be duplicated. They don't have the same sensibilities as our internal data. So I have a read model. I put in a relational database. When I get a new piece of information, I do an update on one column. That's completely fine and optimal, right? Derived data can do all of these things. Source of truth data on the internal store should not do those things. So once I've read from the source of truth, until it changes, I can trust it forever. That's the brilliance of those incrementing sequences. That's how we get all of those benefits of cache invalidation, right? Because I read it once and I save it and I don't care about it. That leads to authority, how to replace three events to start an application that needs historical state from multiple applications. That is why we are saying we define an application. I shouldn't need data from multiple applications to start my application. All of that data should be in one store, or I have two applications, right? That's the difference here, is that's how I define the applications, and that's how I make the system work. So what I should need is why should the public events be treated as transient and allow for duplicates? Wouldn't it be simpler to give them the same immutable semantics as the event store, then you wouldn't have to deal with the replays and idempotency. So when I say duplication, I don't mean republishing the same event ID. When I say duplication, I mean two different events with different IDs can have overlapping data. I can say, invoice updated and have all the data from the first update plus a new outline item. That's what I mean, but don't worry about duplicated data. Every time I update the invoice, I give a new sequence number, and I have a new update. Now it has more data on it, right? So each event isn't going to update itself. We're just going to allow that duplication of the data, which I strongly advised against in the internal model. In the public model, repeat yourself as much as you need. So we're at the end. So additional questions is what I'm here for the next 5 minutes. External events are often transient, not forever persistent, and go through the broker so they can arrive multiple times. Yes, right? I mean, one of the other benefits of having the global ordering on, and if we go back up here, inside of a system, having this global ordering in the event log allows me to deal with replay, duplicate events and missing events in a very simple way. If I have a consumer and I keep track that I've seen event position 9 on the global ordering from an application store, and I've seen every event up to that point, I don't need to worry about seeing 8 again or 9 again. I can just drop it. I don't need to check anything other than one number. And if I see 7 and then I see 9, now I know I missed 8. I can either wait for 8 and jitter buffer, or I can go and do a direct query and go get 8. Then apply 7, 8, and 9, and again, I know where I'm at. So we've also solved a lot of missing message and out of order messaging. We haven't solved, and there's no way to solve it, the problem with not receiving the most recent message. So you do need something else to check your delivery SLAs. So that's most of my content.